A truck cuts through the horizon at dawn. The trailer is sealed, temperature controlled, and packed from end to end. Inside, nearly 20 tons of watermelons sway with each curve, each acceleration. On the outside, it looks like just another shipment crossing the countryside. But inside that vehicle, a precise engineering ballet is underway. One where gravity, vibration, and time are all trying to destroy the cargo. And every decision made by the logistics team is a calculated attempt to stop it. Because a watermelon is more than it appears. It's a fragile giant, large, heavy, and mostly water. Its spherical shape doesn't protect it, it betrays it. Each fruit carries within it a delicate balance of pressure and moisture. If you drop it just 2 centimeters, the damage may not show on the outside, but deep inside, microfractures ripple through the pulp like invisible cracks in glass. Within 72 hours, the fruit begins to rot, and when you move millions of them every year, a tiny miscalculation becomes a massive logistical failure. To understand how they're transported at high speed without losing entire shipments, we need to borrow concepts from unexpected places. The same equations used to model soil compaction in mechanized sugarcane harvesters, which help machines avoid damaging roots underground, are now applied to model the internal shock resistance of watermelons in motion. Their mass, geometry, and water density make them extremely sensitive to vibration vectors, especially in long-haul freight. This is why modern trailers no longer rely on rigid crates. Instead, they're equipped with spring-suspended pallets, floating systems inspired by the damping technology of naval gyroscopic stabilizers. On ships, these systems keep cargo steady during storms. On land, they protect the fruit from micro-movements that would be imperceptible to humans, but lethal to a watermelon structure. It's a paradox of logistics. The faster you move a perishable product, the better, because time is spoilage. But with watermelons, speed increases the likelihood of bruising and fracture, unless the handling, cushioning, and airflow are not just adequate, but mathematically synchronized. Too much tension, and you lose the load. Too much cushioning, and you sacrifice space and fuel efficiency. It's a high-stakes equation that only advanced agricultural engineering can solve. Visualize it. A split-screen diagram. On one side, a naval stabilizer, gently rotating to counter wave motion. On the other, a shock-absorbing pallet, oscillating in real time to dampen trailer vibrations on a rural highway. Different vehicles, different environments, but the same principle: precision in motion, engineering in defense of fruit. And that's just the beginning. Because moving millions of watermelons isn't about picking them up and driving fast. It's about understanding their physics. It's about orchestrating invisible forces. And above all, it's about seeing in each crate a small, perishable world that only survives the journey when technology, logistics, and engineering work in perfect balance. It begins with a drop, not a fall from a truck, not a warehouse accident, just a slight slip of 2 centimeters. From a conveyor belt to a pallet, or from a worker's hands to a cushioned surface. In most products, that would be negligible. In watermelon logistics, it can start a biochemical countdown, because under the thick green rind lies a pressurized pulp chamber, held together by cell walls that burst with internal stress the moment a shockwave hits. The rind might stay whole, the fruit might even look perfect for days, but inside, the flesh has already begun to collapse. Microscopic fractures trigger the release of enzymes. They break down cell walls, feed microorganisms, and accelerate internal fermentation. It's a chain reaction that can't be seen until the damage has already become rot. That's why the industry no longer thinks in terms of visual damage. It now treats each unit as a structurally sensitive object. And in this battle against invisible fractures, innovation isn't about speed, it's about softness, geometry, and absorption. Transport crates have evolved into dynamic cradles, not hard cases or stiff boxes, but soft shell compartments engineered to flex and adapt. Inside them, pressure-dispersing membranes respond like fluid cushions. absorbing shocks and spreading impact forces over the entire surface. Originally tested in papaya exports, these systems have proven ideal for watermelon loads, where a misaligned corner or a sudden jolt can ruin entire rows of fruit. The surprising result is that higher speed doesn't always mean higher damage, if the mechanical protection is right. In a comparative study, two identical shipments were monitored, one at standard highway speed using traditional crates, the other transported faster, but using dynamic floating cradles. The faster shipment arrived with 5% less spoilage, despite harsher driving conditions. Because in that case, the vehicle and the packaging work together, absorbing, compensating, adapting. The concept has taken root in the field. In the Brazilian state of Tocantins, a growers' cooperative redesigned their transport trays after a particularly devastating season of losses. They took inspiration from motorcycle suspension arms, specifically how the rear arm of a dual spring suspension absorbs force both vertically and laterally. Their prototype, assembled with adjustable joints and polyurethane padding, reduced post-arrival rot from 18% to just 6% in less than 6 months of use. And this isn't an isolated case. Across watermelon-producing regions, engineers are now working directly with farmers to design systems not for the warehouse, but for the field, the truck bed, the road curve, the braking pattern, because the fruit doesn't care how far it travels. It cares how smoothly, and in a system where one invisible fracture leads to tons of loss, softness is no longer weakness. It's precision. It's science. Softness is calibration. Softness is control. In watermelon logistics, softness is the only thing standing between a successful delivery and a silent, irreversible failure. Hard surfaces cost tons, and the only way to prevent it is to engineer the exact opposite. A watermelon, once harvested, doesn't rest. It breathes. It generates heat. And when it's stacked tightly with hundreds of others inside a sealed trailer, this process multiplies. What seems like a passive cargo becomes a live biochemical system, producing internal hotspots that rise well beyond ambient temperature. The core of the load can reach 7 degrees Celsius above the outside air, even on a mild day. In that heat, enzymes accelerate, sugar breaks down, flesh begins to soften from the inside, and by the time the door is opened at the destination, the fruit has already passed the invisible line between fresh and spoiled. It's a silent failure, not because the equipment didn't work, but because airflow, true, directional airflow, wasn't accounted for. When watermelons are packed into a trailer, they block their own ventilation. Air gets trapped, heat accumulates, and the cooling units, however advanced, can't penetrate deep into the mass. Without a pathway to flow through, cold air simply circles the exterior. The solution didn't come from the fruit industry. It came from grain silos. Bulk grain storage has long dealt with similar thermal dynamics. Massive, packed volumes generating internal heat. The answer there was a system of vertical ventilation shafts and angled vents that guide airflow into the core of the load. Today, that same architecture has been adapted to watermelon trailers, using vertical chimneys and angled intake ducts to push cool air through, not around, the fruit. It's not just theory. In a comparative study between Brazil and Spain, shipments using forced vertical ventilation showed a measurable increase in shelf life, up to 3.5 days longer, compared to conventional cooling. That difference translates to market value, export potential, and waste reduction across thousands of tons. In the southern Spanish region of Almeria, where heat and high-volume demand perfect timing, a series of test shipments introduced passive vertical airflow channels, essentially open conduits built into the stacking pattern. These channels don't require extra energy. They simply allow heat to rise and cool air to enter naturally. The result? A 9% increase in firmness at arrival and less weight loss during transit, because every watermelon carries its own heat. It doesn't need to be in the sun to begin degrading. It does that on its own, silently, from the inside out. And unless that heat is removed, Unless that biochemical clock is slowed, the fruit will begin to digest itself, even before the journey is halfway through. The challenge is not moving the truck, it's ventilating the cargo. It's creating pathways that cool not just the exterior crates, but the internal pockets where heat nests and spreads. Without airflow, precision cooling is an illusion. Without airflow, time accelerates. And in high-speed fruit logistics, time is not just money, it's mass, lost silently, kilo by kilo, pallet by pallet. A watermelon weighs on average between 5 and 10 kilograms. Now multiply that by a truckload of nearly 2,000 units. Multiply that again by every shipment departing daily from major production hubs like Rio Grande do Norte in Brazil, Andalusia in Spain, or southern Turkey. Then, stretch this flow over weeks of harvest, across highways, borders, ports, and urban peripheries. What emerges is not a simple operation, but a massive kinetic chain, one that, from a distance, appears to be about moving tons of fruit. But at its core, it's about something far more subtle: microcontrol. Modern agribusiness no longer moves food as bulk, it moves it as fragile systems in transit. Each crate of watermelon behaves not as a passive unit, but as a living load. It shifts, breathes, responds to vibration, temperature, and airflow. Logistics specialists now treat each trailer not as a container, but as a mechanically regulated environment, similar in complexity to a mobile lab. Inside it, forces are constantly at play: gravity, thermal inertia, centrifugal stress, and every one of them must be accounted for if the fruit is to arrive intact. This is why the industry has borrowed principles from disciplines far beyond agriculture. For instance, the logic of forage compaction systems, used in balers to ensure that hay is pressed with just enough force to preserve nutritional value, now finds its parallel in watermelon palletization. Pallets are stacked not for space, but for balance. Compression thresholds are calculated based on fruit diameter, skin elasticity, and air gap volumes between crates. Weight must be distributed not just laterally, but vertically, ensuring no collapse or torsion during braking or acceleration. Inside the vehicle, sensors now play the role of silent supervisors. In the Netherlands, a logistics firm has developed trailers equipped with humidity, shock, and load shift sensors, feeding real-time data into an onboard system. When a shift in internal weight is detected, due to a sharp turn or uneven road, the system analyzes the data and determines whether to reduce speed, adjust ventilation, or even redirect the route altogether. If humidity begins to spike in a certain zone of the cargo hold, it could signal the early stages of enzymatic fermentation. In response, the system increases localized airflow or activates auxiliary cooling to stabilize the temperature gradient. It's a level of control that would have been unthinkable 20 years ago. But today, it's not just possible, it's necessary. Because when shipments are measured in hundreds of thousands of dollars, and when consumer markets demand both perfect visual quality and extended shelf life, even the smallest loss becomes a strategic failure. A single percentage point of spoilage, scaled globally, represents millions in waste, not to mention increased emissions and resource consumption. That's why micro-decisions, how tightly a strap is pulled, how far apart crates are spaced, how long a trailer is exposed on a dock, are now fundamental parts of the logistics equation. None of this replaces the human element. On the contrary, it elevates it. Engineers, operators, and agronomists work together to design these systems, not for a lab, but for dirt roads, rural terminals, and unpredictable weather. Behind every truck is a team making real-time calls based on sensor data, field conditions, and export schedules. It's not automation replacing labor. It's technology amplifying human judgment, turning intuition into calibrated decision-making. And there is beauty in that. There is a quiet grandeur in seeing an agricultural product, once handled with bare hands and bundled into open beds, now carried by systems of mechanical elegance, tuned to the unique physics of every fruit. It means that a watermelon harvested in a sun-scorched field in northeastern Brazil can arrive days later, firm and cold, in a supermarket in Rotterdam or Milan. It means that logistics is no longer just about getting from point A to point B, but about preserving living matter across time and space, under pressure, in motion. To the untrained eye, it's just a truck, just a fruit, just a delivery. But for those who see behind the curtain, each shipment is an orchestration, an ensemble of sensors, materials, thermodynamics, and human expertise, playing in perfect synchronization. This is the invisible choreography of modern agriculture, a flow where nothing is left to chance, where softness is calculated, where timing is everything, and where volume alone means nothing, unless every gram is protected by precision. Mass handling in the world of watermelon logistics is no longer a question of how much you can carry. It's a question of how well you can control what you carry, down to the last micro movement. It's not the load that defines the system, it's the system that defines whether the load survives.